Hello and welcome back to Abstract Linear Algebra, the video series where we talk a lot about topics in linear algebra in a general sense. For example, at the moment we talk a lot about general inner products. Therefore, in today's part 13, we will talk about perpendicular vectors, also often called orthogonal vectors. Or more concretely, here we will define what orthogonality means in a general inner product space. Okay, but as always, before we start, I really want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Only because of your support, it's possible for me to create such math videos. And you might already know that you can find rewards on my website, which you find with the link in the description. Okay, then I would say, let's start with a nice picture to explain why orthogonality is so important for us. Just imagine a straight line and a vector x which is not parallel to this line. Moreover, if you imagine that the sun shines from top to bottom, then this arrow would make a shadow here on this line. And indeed, if the sun shines from the top, this shadow here would be smaller than the original arrow. And there you might already know, this shadow is what we call the orthogonal projection of P. More precisely, it's the orthogonal projection of the vector onto the subspace given by this line. And you see in the picture that this orthogonal projection is also a vector. But this is not all, because we also find a third vector here, which we could call the normal component of P. And again, this is with respect to the given fixed subspace here. And now if we call this vector y, we have a linear combination for P. Namely, P is given as x plus y. Now of course, this is not a surprise, because you can always decompose a vector into a linear combination. However, here we want more, because we want to have a right angle between x and y. Of course, this is exactly what orthogonal means here. However, this right angle here should be seen in a general context. It's a general right angle, which means it's only given by our inner product. So you immediately see this is a general and important concept we should put into a formal definition. In other words, it's not a problem at all to generalize our picture here. However, the general definition of an orthogonal projection we will do in the next video. Here we first define the basics, and for that, as always, we need an F vector space V and an inner product. An inner product is always denoted with the pointed brackets here, and you know we have three properties. And now we say that two vectors x and y are orthogonal if the inner product of x and y vanishes. This should not be a surprise for you, because this is exactly what we have for the standard inner product in Rn. And now we just generalize that for any inner product we can have. Moreover, we also use a common symbol here to denote that two vectors are orthogonal. So please remember, the symbol here simply means that x and y in the given inner product give us 0. So you see, this is not complicated at all. And in the picture above, you see we want that x and y in the inner product give us 0. So we could say the picture looks always the same, but the interpretation, the meaning is different depending which inner product space we have. So for example, we could look at a polynomial space again. Let's take the polynomials that are defined on the interval -1 to 1. And then, as we have discussed in part 10, a possible choice for an inner product is this integral here. And now we can just take some simple polynomials and maybe let's call them P1 and P2. And an easy choice would be monomials, so let's say P1 sends x to x and P2 should send x to x squared. Then we can just calculate the integral here. This is not complicated at all, because we just have to integrate x cubed, which gives us by a symmetry argument immediately 0. Hence, P1 and P2 are orthogonal. This means if we see the polynomial space here with the geometry given by the inner product, then P1 and P2 have a right angle in between. So what we take from that is that the term orthogonal now also makes sense for polynomials. Indeed, the only thing we need for this term is an inner product space, which is simply any F vector space together with an inner product. Okay, then let's talk about another important definition here, which is about the orthogonal complement. The assumptions we need here are the same as before, so a vector space together with an inner product. And now for any subset M in V, we can define the orthogonal complement of M. However, usually we exclude the empty subset from this definition. So you see, M does not have to be a subspace at all, it's enough that we have a subset of the vector space. However, I can already tell you that the resulting orthogonal complement is a subspace. And the common notation one chooses is M together with this perpendicular symbol. So the same as before, but now as a superscript. So you might already guess that the definition is not so complicated, because we just take the set of all vectors, and maybe let's call them X here, that are perpendicular to all vectors from M. Hence we can write X in the inner product with a vector M is equal to 0 for all M in M. And this is already the whole definition here. So you see, we just take all the vectors X in V that go into the orthogonal direction of M. So for example, you can visualize that in R3 by taking M as a line. And if that's a line through the origin, then M has only one essential direction. And then the orthogonal complement of M is a whole plane in R3. This means any vector from this plane is orthogonal to all the vectors in M. And of course, it's even easier to visualize if you don't take the whole space R3, but just the plane R2. Then, if we have a line through the origin again, the orthogonal complement will be a line as well. And obviously, it has to be the orthogonal direction here. Moreover, something you might immediately notice here is that in the case that M is a subspace, we have that the dimension of M plus the dimension of M orthogonal is equal to the dimension of the whole space. So you see, in this sense, they complement each other in an orthogonal way. And indeed, in the next videos, we will make this more precise when we talk about the orthogonal projections. So I really hope we meet there again, and have a nice day. Bye bye.